Good afternoon, everyone. My name is Kexin. With me is my colleague, Annie, sitting there. So in this afternoon, we're going to talk about how we designed a real-time next best action recommendation system at Salesforce. So before I go into the actual details of the system, let me give you some context, and the context will start with data. So as we all know and aware that we're going through this very amazing digital transformation where you have all these mobile devices, your laptop, computers, sensors, smart home appliances that's deployed in the world. They're connected. They're sending data to different places. And business these days is facing the challenges, how do we adapt to this, right? Some of the businesses are already starting with this journey, like hotel chains like Marriott. They start to have these mobile devices where you can check in, unlock your room. You can send a text to concierge. They will start to send in your whatever request you're asking for. So and they have like 110 million, I think, rewards profiles, and they can start to serving them in that fashion. So with these unprecedented devices, they have very high processing power, storage, they're connected, and the possibilities start to seem unlimited. And these possibilities start to get multiplied by all these emerging technologies, such as artificial intelligence these days. And Professor Andrew Yang has a saying that artificial intelligence is the new electricity. Well, what's powering and giving these artificial intelligence is actually data. Okay. The researchers, data science researchers and practitioners has already started aware of that data is actually a key to unlock a lot of machine learning and artificial intelligence tasks. This is a research, I think it's a pretty well-known figure that is published almost 20 years ago that is studying different performances of NLP models with different data size. As you can see pretty clear here that the size of data have a huge impact on the accuracy of different models. Even the worst performing model trained with 1 billion records will outperform the best performing model trained, say, like 10 million records. So this also explains why companies like Facebook and Google, where they have these massive data sets, they're leading the research in a deep learning space. Okay. So data really matters in this case a lot. So you may aware of Salesforce as part of the good old CRM system where it helps salespeople to keep track of their customers, their prospects, and to enable selling activities. However, over the past few years, it really has grown to the complete customer success platform with not just sales, but marketing, commerce, platform, services, community. So this also enables us to get a lot of data as well, where you actually see a complete angle of how business and how they engage with the different customers. Okay, so for example, this is just in one part of Salesforce, which is Marketing Cloud. We see a lot of user match queries, data capture events on behalf of our clients. It also sends out about 3 billion emails every single day, and it keeps track of all the tweets, Facebook updates, emails, SMS, push notifications, you name it. So with this data, that really just enables a lot of different applications that's powered by machine learning itself. Just to give you a few examples here is that like email frequency and send time optimization really is to find the ideal frequencies and time to send emails so that as business itself, they can have higher engagement. But as a consumer, these emails or promotions are not that annoying. Okay, so to really get to the topic of today's talk is really about personalization. How as a business to engage with their customers. So in the good old days or still in the small communities these days, business owners themselves will know their customers individually. Like they know their life, they probably interact with them, and they sell them personally so that they can start to give more personalized recommendations or promotions or incentives, whatever. So these will feel much better for driving sales, and it becomes more effective. However, as we start to go with things at large scale, at large businesses with online activities, you don't actually see people face to face. There's no way to actually doing a two-way communication. It becomes very hard. So the challenge is real in this case. So in order to model and help driving this two-way conversation, we can really just separate two kinds of different events, where the first type of events is called activity, where they are customer-initiated events, like maybe go visit a website, going to a bank's branch, I can call the customer service. So these are customer-initiated. At the same time, the business may initiate certain events, like what we call them actions, where at some time they can send you emails, and they can, when you visit the website, they can give you recommendations, they can send you promotions, or different pop-ups to say, hey, maybe you want to try that. So these are two different basic activities, or we call it events that we can model. Sometimes there are overlaps, we call it an interaction, sometimes they don't. But these are really just the basic building blocks of how such a system can be built. With this in mind, then whenever there's an overlap between an action and activity, you have a touch point or an interaction in our case. So based on customers, you have, like, we're all different. We all prefer interacting with businesses or even individually very different ways. Some prefer like the short and sweet things. I just wanted to get this done today. I know exactly what I want, just give me that. And some will maybe just want to know a bit more. They're less confident, or they may prefer to do a lot of research before they're making a decision. So these journeys will be very different, and you want to engage customers with very different ways. So they will all go through the same phases: awareness, consideration, purchase, service, and eventually some may become loyal customers. But how they actually go through this journey could be completely different. So you need a system to be able to drive and send them different type of messages. So this is what we call the next best action system. So at Salesforce, there's a tool called Interaction Studio, which basically just help people do exactly that. So how do they allow these reporting tools? You can see how customers engage with all your potential touch points you can check. There's different side of like reporting tools to see where they drop off, where they start, things like that. And what marketers do these days is they start to analyze on other users, maybe segment them into different kinds of group by different criteria. And then they have a set of actions they could utilize. The actions could be ads, it could be emails, it could be recommendations, it could be certain incentives. And then they start to see and think about how you can combine them at different stages to send to the users. But they don't know how to do that based on different profiles, so they have to try different options. And then when they can design some A/B testing scenario to see which are more effective, which are not. And in the end, they may learn something that applies to a certain set of customers and deploy whatever strategies they have learned. So on the paper, this seems like a fine approach, right? Based on data, you learn behaviors, and then you deploy whatever is working based on what you see as a result. However, there are three key difficulties, the three key challenges in this case. The first of all is think about the action space. You may have tens of them, but in terms of how you're sequencing them, how you combine them, that you goes to the combinatorial space, which is ginormous. Even you start to understand and are able to eliminate some of them, you will need someone who really understands how statistics works to be able to design all these A/B testing scenarios, to be able to actually generate the insights that tells you inference. So even after that, say you export everything, you deploy your perfectly designed A/B testing scenario, it takes a lot of time in order to have the results. So in the end, you may have a perfectly working solution, but what you learned is what was working for the past month. After that time, things may already changed due to seasonality, and maybe your business objective also shifted towards another goal. So these are the things, is like it's very hard. It's a big challenge. However, if you think about this, right, these tasks are really mundane. There's a fixed approach to this, and the goals is pretty well established. You have certain things you want to maximize, and you have a set of possibilities that you want to explore, and you just need to try these different combinations. These are mundane for human analysts. However, these are really that's what machines do best, is to see these boring tasks, identify patterns, and then start generalize certain rules. So in this case, the problem really is to find some certain policies. We call it pi, which is a rule to say, given a user and their current context or stage they're at, and the return action, in the end, it will maximize the general rewards you can define. It's as revenue or whatever based on your business. Okay, so you have that. So one typical approach a machine learning practitioner will do is, well, I have historical data. I know how they perform based on different actions we may have designed in the past based on certain business rules or certain strategies you've chosen before. And we just train a classification model and return that. Right. However, this won't work in practice. The first of all is you will not be able to get the feedback for the actions, for new actions. Right? You may have a new set of things you may want to push, and these feedbacks are just not available. And also, it will be biased towards what the analyst has been designed in the past. So what the model learned basically is try to mimic the past behavior rather than improve and explore the space, the action space. So that won't work. However, we could do much better than that. So if we carefully examine what people are actually doing today, by analyzing behavior, explore action space, try, deploy, and apply in simple terms, given a context, explore, learn, exploit, and go through the cycles again and again, try to refine and improve overall. So this does sound like a very actually well-defined and studied problem called contextual multi-arm bandit. For those of you who's not that familiar with contextual multi-arm bandit, the problem setting goes this. You have a fixed set of resources. You may not know how much reward you will return. And the problem is, given certain rewards, you know the rewards, the problem is, how do we define and utilize a strategy so that overall we can balance between the learning and the exploitation? So this is a classical reinforcement learning problem that exemplify the rewards versus, the exploration versus exploitation scenario. So you pay a price to test out different things, but at the same time, you may have the risk of deploying whatever things that may have a much higher reward. So a simple strategy could be, I can simply just shifting between times. So for day one or the first hour, I'll try to throw out actions randomly and test out and collect data. And then the next hour, we use whatever we learned from the previous hour to return the best action that has been learned in the previous hour. So that's a fine strategy. Or you can split the users too. Right? You have a set of users that you clearly just don't care about. That's your control group, and use whatever you learned from that subgroup to drive more revenue from the rest of the group. Okay, so that's a fine starting point we can start with, but clearly we can do a lot better. So the basic scenario, the basic intuition is that for the things you don't know about, you probably want to give it more chance to show where the actual rewards are, or the probability of return of rewards are. For the things you already know, you're pretty certain if they have a higher reward, you can start to give that option more chance. So here becomes a balance. One typical approach is called upper confidence bound, and the scenario is, well, I can before I know anything, I can probably calculate what is the optimism time. So given if I don't have a lot of data, all of them will have high probability, higher confidence bound. So I can start to send data, to send the actions with a much higher confidence bound. And then over time, when you start collecting data, the confidence bound will shrink, the alpha confidence bound will shrink as well, so that you can start to balancing between the actions with more data and actions with less data, but higher bounds. Okay, this is a deterministic approach. You can also use a probabilistic approach, which is called Thompson sampling, where you start to model different actions with their probability distributions. So you have a prior distribution, starting will probably be a uniform distribution, and then when you collect data, you start to seeing the peak, and you sample from those distributions, and basically sampling technique will help you balance between which actions you can choose in real time. Okay, so that is what you can do right now with existing techniques. However, clearly, it did not really work given the actual scenarios we're dealing with. Now, Annie was going to talk about a few challenges we actually start to applying them and play with real data.
So on a high level, the system receives activity and context from the environment, and then it uses it to generate the next best action to take, and then return it back to the environment. And after the reactions to the recommended actions are observed, they're feed back into the system to update the policies. So the policies can be updated after each iteration or periodically depending on the need and computational cost. So overall, this is an interactive system that learns automatically from the environment as being used. And then from a user point of view, a policy is basically a machine-learned mapping from the feature space to the action space. It can distribute users across different actions that can maximize the overall reward. So initially, this standard contextual multi-embedded model works pretty well for us. However, as our problem becomes more complicated, very quickly we find it hard to tackle a few challenges. One key challenge is that when we have multiple objectives that we want to optimize for, it is very hard to design a single reward strategy that can work for all. So for example, we want to optimize for single ticket purchase and also seasonal ticket purchase. And we may also want to increase the user engagement and perhaps move users forward in their stage progression as much as possible. And then it becomes very tricky to mix all these different objectives together. And it might be relatively easier if we can obtain the relative weights that can measure the importance of different objectives. For example, if we know the dollar value associated with each objective that tied to the revenue, it may work to combine them together according to the weights. However, if we don't have that importance weighting, then it becomes very tricky to combine them together. And then it becomes even more problem when the different objectives are not even in the same category. So in this case, like ticket purchase and the stage progression are not even in the same category. So that it's very awkward and not intuitive at all to mix them in anyways. And another challenge is when faced with multiple objectives, it is quite hard to minimize the counterfactual regret. So assume that we can get the importance weighting for different objectives, and then we know that goal B is more important, so that we reward it higher. And then it is very likely that more users will be recommended actions towards reaching goal B. But in reality, this may not be the case, because for some users, they may have a much higher chance of reaching goal C, although it is rewarded lower. And for some users, it may have a very little chance of reaching goal B, although it is rewarded higher. So in this case, we may end up with much larger regret due to this kind of lack of personalized recommendation. So in order to handle these challenges, we designed and built a hybrid contextual multi-Bandit model to handle different objectives, and further built a propensity score on top of it. The propensity score serves as a policy selector, and it picks the personalized policy for each specific user according to their different unique characteristics. And this hybrid multi-Bandit model consists of multiple policies, and each policy is optimized for one or more objectives depending on the characteristics. So this hierarchy structure provides us with more flexibility when our problem space becomes bigger, and it can easily be extended to handle more complicated use cases. So in our use case, we trained a standard multi-class classification model that takes users' entire history as input and extract the user's profile affinities, their behavioral patterns and intent, and then use it to predict which goal or goal category has the highest chance of achievement by a specific user at the moment. And then the user is fit into the corresponding policy to generate the next best action to take. So with this propensity score, we're able to find the best path for each user according to their interests, their behavioral patterns at the moment, and instead of always picking the highest rewarding policy. And then this hybrid multi-Bandit model allows us to handle different objectives more accurately and properly. So there are many types of multi-Bandit model algorithms. We use linear models for some policies and nonlinear models for others. And all the policies utilize Thompson sampling to balance between exploration and exploitation. So since the data we have are time-sensitive series of events, we can't really shuffle our data set and do cross-validation as what we usually do in standard classification or regression models. So instead, we designed this rolling valuation method to better simulate what would happen in reality. So in order to do that, we start from the beginning of our data set and train the model with an adjustable window of data, and then use it to predict the next time window. And then we roll forward and repeat this process and roll forward again until we reach the end of the time series. And then we get these batches of predictions, and we compare the predicted action and the actions taken in reality. And then if they agree with each other, we call it a hit. And then that's the overlap area. And then for all the hits, we calculate the weighted average, predicted score, and the observed rewards. And then that gives us a measurement of how close our model represents the real world observations. And further, we also calculate the overall expected reward and the overall observed reward. And then comparing those gives us a sense of how much counterfactual gain one can expect. So now we know how the system is trained and evaluated. There are few dimensions can be configured and experimented in the system. So first of all, the training window size determines the model quality. And then the shorter window will give us a system that's more reactive to new changes and adapts more quickly. And then a longer training window will recommend more stable and robust recommendations. And on the other dimension, one can choose to exploit the best performing action to maximize immediate gain or to explore other possible actions to gather more information for now.
So in order to implement this, so there's a couple of things that needs to be aware of as well. So in a typical scenario, you would expect whenever you perform this prediction, each interaction you would be able to learn by observing the feedback as well. However, in practice, it's not possible. You send out the recommendation, and you will actually learn from after the fact whether they took the action or not. That's very typical. So when you implement this, you want the recommendation to be separate from the training service. This also have another benefit as well, because typically when you deploy this kind of a system in the wild, customers are not that confident it will perform, so they tend to be a bit more cautious. And there will be other set of customers that's actually not using your recommender as well. And there's no need to throw that data away. It's actually is still very valuable. So that's the other part. And also there are things that's just not online. There are places you can send these pings, these trackers, and send to the system. But there's certain aspects of offline, like you visit a dealership and they record whatever things afterwards and then upload the data afterwards. So these requires a batch capabilities. So that's one reason why we actually do need these to be different things. And also in terms of serving in real time, you can't perform these feature-based calculations every single time. They need to be updated asynchronously so as well. So you will need a feature store for all your all the known users. That needs to be updated by a different system, but used with online system to do the recommendation. All right, just some highlights in terms of technologies we've been using for the training. We've been as a group using Spark a lot in our cases, so there's no brainer to use Spark. We also have a pretty good streaming capability. It has pretty good batching capability, and the code you written is not that different anyway. So that is that. And feature store, you want very fast updates. You want the reads to be fast as well. So a database like Cassandra work pretty well in our case. So we're using everything in AWS, so that's the DynamoDB, which is almost the same. In fact, Cassandra is inspired by the DynamoDB paper initially, I think. And the service is just standard web service. It could be implemented by anything. We're using Play because we're using Scala in general. I hope there's something useful that you learned today, and thank you very much.